Okay, so now we're ready to start our discussion of differential geometry for general surfaces. We've taken a look at Euclidean geometry in 2 dimensions and spherical geometry on the surface of a unit sphere. And we've looked at some of the concepts that we're going to generalize now to the general case. And so let's get on with it. I think that we picked out those parts of Euclidean geometry and spherical geometry that act as an inspiration. And we'll see that some of those simple ideas that seem so elementary and obvious, well, when they're generalized to curved surfaces, really result in interesting and deep results. We'll see that, for example, the Gauss-Bonnet theorem is a result of generalization of ideas that we've already discussed. So here I am in the geometry of a curved surface, and on the curved surface I put down a mesh, a two-dimensional system of coordinates. They're not necessarily, they're not necessarily orthogonal or anything like that. Just an adequate mesh. Okay, as we discuss in the textbook. Remember, in the textbook by Manfredo di Como, you'll find all of these expressions done with all the statements perfectly correct. We're emphasizing here fundamentals and intuition, and so we'll be satisfied with more informal discussion. But we certainly do recommend that great textbook. So here I am, and I have a point P and I have a point Q, and they're infinitesimally close to one another. I want to take a look at the intrinsic properties of the surface, and that's the metric, sometimes called the first fundamental form in classical differential geometry. So I'm going to look at the distance between nearby points, and so I'll write the difference, the distance between the 2 points in this coordinate system, and so dr is dr by du. Remember, the sub u indicates differentiation by the variable u, and I'm just writing this differential down in the coordinate system uv in the appropriate fashion. Okay, so dr is r du du plus r dv dv, and here's the differentials in both the u and the v direction. So that's how we'll set up the problem. And in many cases, I'll have explicit formulas for r, and I'll be able to evaluate all of this stuff. So I look at the distance squared between 2 points. R squared is a dot product of dr with itself. And then I write it down in this coordinate system, and I have to take this dot product. Okay, and so I do that. I get 3 different contributions. I get a contribution that goes like du squared. Its coefficient is called E. That's a dot product of R sub u dotted with R sub u. Okay, easy stuff, just write it out, little linear algebra to do. The cross product between du and dv is called F. Okay, and that's R sub u dot R sub v. So so I think of R sub u as a tangent vector to one of the coordinates, and R sub v as a tangent vector to the other one. And so I have a visualization and an intuition into what these objects mean. For example, if I had an orthogonal coordinate system, then these 2 vectors, which lie along the coordinate axes, would be perpendicular, and so f would be 0. Okay, in many cases of our applications that will be the case, but we'll write out our formulas in the general case. And then I have a third term, g dv squared, and g is just the differentiation of r in the v direction dotted with itself. Well, once I have the metric, okay, and we'll always write the metric is dr squared equals e du squared, etc. Okay, where e and f and g are given by those inner products. Now I know how to measure distances. Therefore, I know how to measure angles as well, because angles I can make from dot products of distances. Okay. So, for example, the arc length of a curve, r of u on s. So I might have a curve on this surface in some particular way, in some arbitrary difference way, and r might be parameterized by a parameter t, okay? So t might be the arc length or whatever else is convenient in the problem. And we'll see situations where t will be all sorts of different formulas, different cases, okay? Just depending upon the particular application. I can go from one application to another and just choose t to be useful. T in my case of polar coordinates might be an angular variable. T in other cases might be the arc length. T in other cases might just be the x coordinate, whatever. Anyway, the arc length of a curve in S is just the integral of the differentials of length as indicated there. I'll let these be rather schematic. I can write that then as dr by dt times dt. So dr by dt is the tangent vector to the curve. Okay, I need the magnitude of the tangent vector, and I can write that as a square root of the square. And that's useful because then you see I get dr dot dr, and that's my metric. Okay, and downstairs I have dt squared. So here in the metric where I had du squared, it becomes u prime squared, where u prime indicates du by dt. The prime indicating differentiation as we set up the convention in this lecture series. And so here I have the metric differentiated with respect to t, and then dt, and I can calculate the arc length that way. So you see, given the metric, I can calculate arc lengths, I can calculate angles, and all sorts of things. Okay. Another thing I might want to calculate, and this will be critical in our applications, is the surface area of regions of a general curved surface S. Okay. Well, to do such a calculation, let me look at the infinitesimal element of area. Okay. So if I use a mesh u and v, then along one direction I have a vector of length r sub u du. In the other direction I have r sub v dv. Okay. Well, then I have the area of this parallel pipet is just the cross product of those two vectors. Right? We're just taking what you know from vector calculus and applying it in this particular scenario. So it's just this cross product. The scalars, the u and the v, can be pulled outside, and I see it's just the cross product of r sub u with r sub v. R sub u and r sub v are tangents, okay, to the surface at that particular point. They span the tangent space at the point P right here, okay, and they'll play an important role in everything we do. Okay. In particular, I can write the area in terms of the metric. I certainly expect that to be the case. If I know the metric of a surface, I should be able to calculate more complicated things like area. So let's do that. Well, here I need the magnitude of dr cross dv, and so there are many ways to do this, but I might look at the magnitude squared of it and add to it the magnitude of the dot product of the two vectors. Okay. Well, the magnitude of the square of the cross product is the product of the magnitude squared times the sine of the angle between the two vectors. And then, similarly, the square of the dot product of the two vectors is the product of the magnitude squares of the vectors times the square of the cosine of the angle between the two. Okay. Well, so that's what I've done here. Sine squared plus cosine squared is 1. And so on the right-hand side, I just get the length of r sub u squared times the length of r sub v squared. Okay, so then I can solve for what I'm interested in, this cross product, magnitude of it, and I see it's the square root of this collection of objects, and lo and behold, that collection of objects is just components of the metric. R sub u quantity squared, well, that's just e in the metric. R sub v quantity squared is g, and then the cross product of the two squared is f squared. So I see that the differential of area is the square root of eg minus f squared. We'll refer to that as the square root of the determinant of the metric, okay, because we'll be writing it in the form of a 2 by 2 matrix. okay? And so that'll be the appropriate expression. It'll be the determinant of that metric. We'll check that in a minute. And then I can calculate therefore areas by doing the integral over a region of the surface parameterized by u and v by weighting the du dv by the square root of the determinant of the metric. Okay. Okay, now another quantity of great significance to the surface is the normal to the surface at the point S. Well, we have two tangent vectors, RU and RV, okay? And for a good mesh, these two vectors are going to be in different directions, and so they're linearly independent, and their cross product will be different from zero, okay? And their cross product divided by the magnitude of the cross product is a unit vector, and it's normal to the surface, right? It's normal to the surface because n dotted into either of the two tangent vectors is zero, because the normal is in the direction of the cross product itself. The magnitude of the two vectors, r sub u and r sub v, is just the determinant of the metric, and so I can write everything down like that. Okay, and n squared is equal to 1, so that's particularly useful. So at any point on the surface, I have a natural triad. Okay, I have the tangent in one direction on the mesh, tangent in the other direction on the mesh, and the cross product being perpendicular to the surface at that particular point. Okay. So the normal to the vector plate is very significant, and it defines the Gaussian map. Its derivative is called the Weingarten map, and we'll get to that soon. But to understand the shapes and curvatures of surfaces, Gauss imagined putting a pincushion on the surface. So in particular, in the case of one of our spheres here, I could imagine a pincushion of normals to this surface, all pointing out and indicating a direction. Okay, and so it's clear that my unit vectors over this surface, the way they change as a function of the distance along that surface, is an indication of the curvature of the surface. And we'll be pursuing that idea, and that's one of the important ideas of Gauss, the relationship of the rate of change of the normal vectors along a particular curve, indicating the curvature of the surface. And we'll make that construction quite explicit soon. So here's n, it's a unit vector, and here it is at the particular position P. And then I'm imagining the normals at various different points on some general curve, surface S. It's not a sphere, it's just some general curve. And so here it points in this direction, over here, a little different position, it points in this direction, and in this direction, and in this direction. And then Gauss said it would be profitable to take all of those normals and compare them. Okay, so I'm going to map them to a common origin and keep their directions unchanged. So n of p will point in that direction. I've done that over here, where I've just translated all of the four vectors to a common origin. They're unit vectors, so all of them sit on the surface of a unit sphere, s squared. So this is a mapping from the surface to s squared implemented by the normals. Okay, and you see the various normals here populating the sphere. Okay, and we're going to want to understand the systematics of that map, because it's going to tell us a lot about the surface. It's going to tell us both how the surface is embedded in Euclidean space, R3, and it's also going to tell us about the intrinsic properties of the metric, of the surface itself. What was the inspiration for this construction? Well, you should know, of course, that Gauss was a great mathematician, but he was also the director of an astronomy institute for much of his career. Okay, he spent a lot of time dealing with with telescopes. And what's the characterization of telescopes? Well, it's a direction in which you look. Normals, okay? So it's a natural construction from the perspective of an astronomer. That's what you learn. That's how you characterize the universe. What direction do you look at to see a particular object in the sky? Perhaps the planet Venus or whatever. Well, of course, in the case of Gauss, he was famous because he was the one who predicted the orbit of the asteroid Ceres. Okay, there was an asteroid which was observed for a very short period of time, very limited data on it, and then it passed on the other side of the sun, so it was out of view. And then the problem of the day was when will it appear on the other side of the sun and at what position? Well, Gauss took the limited data that the astronomers had on the asteroid Ceres and used approximate mathematics, okay, ideas in linear algebra, curve fitting. He had to take into account statistics as well. He had only a limited number of points. He had errors on all of those points and errors on the curve fitting he might do to it. He invented the idea of Gaussian normal distributions in the course of trying to predict the orbit of Ceres. Okay. He invented a great deal about statistical analysis and error analysis because he wanted to come up with a prediction of where Ceres would be when it came out, when it was visible on the other side of the sun. It's a complicated problem because you were seeing you had measurements on Ceres from the perspective of the Earth. Okay, but the Earth is orbiting around the sun, and you want to understand when the Ceres is going to again be visible from the perspective of the Earth as it orbits around the sun. Okay, and Ceres orbits around the sun, disappears on the other side of the sun, and then appears coming out. So there was a great deal of geometry to be done, and Gauss was the one who did that with great fanfare. Okay. He was famous in his day for being the mathematician that predicted the orbit of Ceres, a very challenging problem that was the inspiration for a great deal of mathematics, of curve fitting and statistical analysis, as well as geometry, as well as applications of Newton's and Kepler's laws of planetary motion. Okay. So he wanted to consider, back to differential geometry, he wanted to consider a curve, r of t, on S. So I'll write r of t in terms of the coordinates u and t. Okay, and so as the point P moves along the curve, I can parameterize that as u of t and v of t moving along the curve. Okay, so our emphasis is naturally drawn to the rate of change of the normal along that curve, and that's called the Weingarten Map. Okay, so we're going to want to understand the Weingarten Map, okay, because like I said, it's going to tell us a great deal about how the surface is embedded into three-dimensional Euclidean space, as well as the shape of the intrinsic surface itself. Now n prime lies in the tangent plane. Why is that? Well, this is one of those equalities that we're going to be using again and again and again, and this is a kind of generic derivation that we'll use again and again and again. We notice that n is a normalized vector. Okay, it equals 1. If I differentiate that with respect to the parameter, then I learn that n dot n prime is equal to 0. As n moves, it preserves this normalization, and that will only happen if n is perpendicular to its rate of change. Okay, so n prime therefore lies in the tangent plane, and we can think of n prime as a linear operator on the vectors of the tangent plane. right? You would write for n prime just using the chain rule, that n prime of t is dn by du times du by dt plus dn by dv times dv by dt. Just the chain rule, like that. But now you've separated the problems into two bits. You have these derivatives of n in the two directions. That's one calculation, and then you have the details of the curve itself, u prime of t and v prime of t. So you have the derivatives of n in the mesh, okay, times the rate of change of the curve along the surface. But you see, then I can think of n prime as a linear operator on the vectors of the tangent plane. N prime lies in the tangent plane. I write it like this, and I see that n prime, okay, gives me a linear combination of u prime and v prime, and the coefficients are properties of n itself. So it results as a linear operator on the vectors of the tangent plane. Okay, that's how I want to think about n prime. It lives in the tangent plane, and I want to think about it as what it does in there. Well, first of all, we notice that it's self-adjoint and is therefore diagonalizable. It's an operator. I'm going to write it as a 2x2 matrix eventually, but before I get there, I can think about it in a more general, abstract, geometric fashion. Okay, and I'll do so using what you guys know about linear algebra. Okay, well, we'll see that it's self-adjoint, and therefore it's diagonalizable. We'll check that in a minute. So it's going to have a couple of eigenvectors. I'll call them E1 and E2, and it'll have corresponding eigenvalues K1 and K2. So when n prime, okay, is calculated in the direction E1, it reproduces the direction E1 with a magnitude of K1, the eigenvalue. And similarly in the direction E2. That's the meaning of a diagonalized linear operator, and the meaning of an eigenvector and an eigenvalue, as everyone knows. Okay. Now we also know, since I claim it's self-adjoint, that the eigenvectors are going to be perpendicular, and that will simplify my life a great deal. And in most of my applications, there'll be a K1 and K2. That in general will be different. On the sphere, they're going to both be identical in the value of 1 over the radius of the sphere, but in general they're going to be different. And I'll typically take K1 to be larger than K2. To show that the operator is self-adjoint, I'll want to show that the dot product of n sub u in the direction r sub v is equal to n sub v in the direction r sub u. Then it's self-adjoint, right? That's the condition of self-adjointness. It's that the off-diagonal components are equal. Okay? Okay. So if you're a little rusty on that, look at your linear algebra and verify that. But also, we're going to come down to 2x2 matrices soon, and so I'm sure everyone will be more comfortable than our general discussion here. The proof of that is again one of these many statements that we'll use. Okay. To take a statement and differentiate it and deduce something about the directions of the vectors involved. In particular, the normal vector dotted into either of the tangent vectors is 0. Right? N is normal to the surface. It's perpendicular to the tangent vector, so those things are 0. Well, if those things are 0, then I can differentiate either of them. I'll differentiate this fellow here with respect to u. Okay, so I'll get two terms, and I guess I do it with respect to v. Oh, I'm sorry. So I'll differentiate with respect to v, so I'll get n sub v dotted into n sub u. That's one term. And then the second term, n dotted into r differentiated in the u and the v direction, and that sum is equal to 0. The derivative of this, of either this or this, has to be equal to 0. N dot r sub u is 0, so the derivative is certainly also equal to 0. So I'll differentiate this fellow with respect to v, I'll differentiate this fellow with respect to u, and then I'll look at them. Well, I look at them and I see a term on the left-hand side which look identical. Well, yeah, r differentiated with respect to u and then v is the same as r differentiated with respect to v and then u, right? Ordinary differentiation can be done in any order you wish. That's ordinary differentiation. So those two terms are the same. Well, if those two terms are the same, of course, then then this guy is of course equal to this guy, and that's the proof. Okay, that n sub v dot r sub u is equal to n sub u dot r sub v. Switching the indices around, I get the same thing. Okay, okay, and so I know that that n prime is now self-adjoint. Okay, so we're going to take that property, okay, and we're going to use it to discuss the shape of the surface as it's embedded in 3 dimensions. That's a study of the second fundamental form of differential geometry. The first fundamental form being the metric intrinsic properties of the surface. The second fundamental form asking the question, well, how did you embed that surface into 3 dimensions? And that's the subject of n prime, and we'll do that quantitatively starting next time.